we discussed about real-time operate scheduling algorithms. The top most used algorithms are rate monotonic and EDF. The research is going on, there are few variants those have been added for real-time scheduling. But all of you now know that what is a real-time job. A real-time job are the task is one which could be periodic and other could be aperiodic or sporadic, but each and every task would have a deadline associated with it. So it means that there are some results if that particular the task is not completed within that particular time. So that is an additional parameter added to each and every task, which is called real time, and it has to be responded in a timely fashion. We know there are different types of tasks. Some are given priority based on their CPU burst. Some are given lower priority because there is more CPU time they want. Some are we need more responsive, and that's why they are given more priority. Just like on your mobile phone, you need your mobile phone to be responsive. So the tasks which are running foreground, they has to be executed at the top priority as compared to those processes which are running as in a batch or backend processes. So there is not a one class of processes or threads are running in your operating system, but there are multiple type of processes running. So the approach is basically creating multiple hierarchy uh, queues, and based on the queue, the each and every task would be allocated to CPU, and within the queues we can increase and decrease the priority of a particular process, so that its priority is always given, it is always given a chance to be executed. As we discussed about aging is basically as a process that keeps on waiting and a low priority process, we try to increase its priority as the time passes on, so that it eventually gets its turn to be executed onto CPU. So the one we discussed here is rate monotonic scheduling, and other is EDF scheduling. But before I go here, I just wanted to showcase the previous algorithm that we discussed. I think in the last lecture I wasn't able to clearly showcase what exactly I mean to show you. If we remember, we discussed about there are two commands that I want to tell you, and this is the, let me open the make file here. So this is the make file that has been created for different scheduling algorithms. So there are FCF, so first come first serve scheduling algorithm, then we have round robin algorithm, and then we have priority algorithm. So this is scheduling priority, and then we have scheduling priority round robin. So these are, and the last is scheduling shortest job first. So these five, so basically 1, 2, 3, 4, 5 scheduling algorithms are there. We will see how they will actually respond. So just to give more insight onto makefile, so each makefile would have targets. So now we would be running target. Now each target would require some other files to be executed. So you can see driver, this would actually load your file. Then the list.o, this would actually be running this particular target where list.cc would be executing. So this file would actually create a linked list. The CPU file would actually be allocating your job one by one based on the schedule which is mentioned here. So let us see what jobs are there. So the jobs here are basically these are the jobs which we want to run. So task 1, which is having priority 4 and the CPU burst of 20 millisecond, and then task 2 is basically having priority 3, and then it will be running for CPU burst of 25. So let's run first. Is a first come first serve algorithm. So now see it. So this is how basically jobs would be running. I think as why T8 is at top, because we are creating a linked list and head is moving toward the last link which is added. So your link is at this, so it keeps on popping from the head and then start scheduling those particular jobs. So this is first come first serve scheduling. And then we have so in shortest job first, the order is basically changed, so based on the job size. So you can see the CPU burst cycle for T6 is smallest. So this is first is executed and then others are executed based on the CPU burst cycle. So this is how the jobs are being executed. Then next we have priority. Let me pass in the value. So based on the priorities, they are actually executed. Then we have round robin, and similarly now round robin would be something better result. So this is how the tasks are allocated. And then we have priority RR. In priority RR, what is the basically scheduling algorithm is that the priorities would be given to tasks based on the priority of the task. And then if the priority of the task is same, if two tasks have a same priority, then they would be executed by round robin. So round robin unit is quantum time is 10 units here. So you can see the task T8 would actually start executing, and then we have task 5 and 4. Those are having priority 5. So those actually started executing simultaneously using round robin approach. So once the task 5 finishes, the task 4 would actually finish. And then here you can see there are three tasks, 7, 3, 2, which are having same priority of 3. So they are now executing by round robin. And once they finish, this is finished, the task which is having lowest priority is finished. Now here the priority is basically higher the number, higher is a priority, lower the number, lower is a priority. This is basically how the jobs are being executed. Now this is what I wanted to show. In addition to it, if we want to look for the scheduling of a real-time process, if we remember, there is a PS3 command that will showcase all the processes those are running. So if I do, then it'll show me all the processes and their IDs along with their threads. So here you can see Snapped is basically a process with process ID 867, and it has a number of threads running for it. Now if I want to see what scheduling approach and algorithm is used, then we have a command chat. So we can look at using man. So it manipulates the real-time attributes of the process. So we can see the process and manipulate the real-time attributes using this command. So this will be actually showcasing me AP is for P is for process, A is for showing the attributes, and then I'm giving the process ID 67687. So we can see the scheduling other. So there are three algorithm types, those we discussed in earlier lectures: scheduling FIFO, scheduling short RR, and scheduling other. So all threads on this system, on this Linux, are running using scheduling other scheduling policy. There is another command that would actually help us to look at the CPU affinity that is basically task set. So the task set would actually allow us to look at the CPU affinity. We discussed about that during load balancing, we try to minimize the shift, because we want to take care of the which are like the currently running processes which are having already populated cache memory. So we ask the process, okay, if there is any affinity to any processor, they can we can define it. So this task command is basically used for that. So let's look at the process affinity of 867. So everyone is having basically affinity to processor 1 here. So when we have multiprocessor environment and multiprocessor system, there might be more than one answer coming to it. So because we have only one, so that's why the one is coming. So all have affinity to run on CPU one. So this is basically how we can see different attributes. We can use these variables into our program or scripts, and then get advantage of this particular thing. Okay, so now in rate monotonic, we discussed about scheduling. When the jobs are coming, each job would be having three attributes attached. So those attributes are basically the time, the CPU burst, then we decide based on this, we have deadline, and then we have periodic. Here we are just considering that the tasks are periodic, and for your basically rate monotonic, we consider that the priority of the task is based on the period that is coming. So 1 by p is basically the priority that is given. Rate monotonic scheduling algorithm is a static algorithm which just assign the priorities based on the period of the task, because the periodic task and it is fixed. So there is no priority change over the time when there is a criticality in the deadline. So we discussed few scenarios here. So we discussed here, if we remember, in this case, what we discussed is if P1 is of having an period periodicity of 50 millisecond, and P2 has periodicity of 80 milliseconds, where T1 is the CPU burst of 25 millisecond and T2 is of 35 millisecond, and we have the priority P1 has priority than P2, so it will start executing. P2 would actually execute for 25 millisecond, and then it is preempted or interrupted by P1, and P1 would start again executing. Here this bunch 10 millisecond is basically is a conflict area, because at 75 millisecond, another iteration of P1 has just finished its execution, and P2 is allocated to CPU, but the remaining CPU burst for P2 was 10, and which actually crosses its own period. So at this particular time, from this 80 millisecond onward, there are two P2 instances or processes, those would be existing in the queue or ready queue. So this particular situation is called missing deadline. So deadline missed. So here this situation, the deadline is missed because P2 did not get enough time of CPU so that it could be executed to its completion. And why that has happened? Because you can see here, then we calculated about the CPU utilization. The CPU utilization for these two processes is for P1 is T1 over its period, for P2 is T2 over that their its period. Now that is basically CPU utilization. I make it like CPU CU 1 and CU2. So total utilization become 0.94. This 0.94 is higher than the worst case scheduling that could happen, or utilization of CPU. So the worst case CPU utilization for RM algorithm is 69%. So it means that if there are a number of processes, those could be executed by RM algorithm if their CPU utilization is smaller than 69% of the approaches. So that is basically used, but still it can go up. That is worst case, and it can still go up. So in the other last case we discussed, the utilization was 94%, and that's why it is not able to actually execute and missed the deadline. In such situations, EDF, which says that it could actually allocate the processes to 100% utilization. So because it is, first of all, it is a dynamic allocation or scheduling algorithm, because it schedule the jobs based on the deadlines rather than the fixed period of the job. So earliest deadline is earlier the deadline, higher is the priority. So it basically, whenever a process is allocated or added to the ready queue, it would always look for the deadline, the pending deadline of the process, and based on that the priority is given to that. So in the same situation, what would happen, the same case what we have discussed earlier, P1 is allocated, then P2 P, P1 is P1 is allocated, P2 is to be allocated. Now at this particular time P1 entered into the queue, and here the pending time, the deadline is 10 millisecond, and for this we have, the deadline is of 25 milliseconds, if I say, because it has 25 milliseconds time burst. And even the deadline for this is because this is added at 50, so the last time that we should execute P1 is 100. So it has more time than P1. So at this particular point, based on the deadline of the processes, the next preemption would be selected. Thus, at this particular time, P2, the deadline would be smaller than P1's deadline, and based on that P2 would be assigned higher priority than P1. So that's why no preemption has actually happened, and P2 continue to execute, and once it actually execute, P1 then started, and we can see there are no deadline misses here. So in this case, when so whenever actually your process become runnable, it announces its deadline, and based on the adjusted deadline, the priorities of the task and the processes would be checked, and based on that the preemptions would be handled, and jobs would be allocated to CPU. It's dynamic because it will check for the deadlines, which process deadline is closest, and based on the closer the deadline, higher is the priority. So this is a dynamic priority because we never know what would be the priority on runtime. So your RM is basically static priority. Okay, each task would come with its attribute that this is my periodicity, and your RL algorithm would assign, okay, P1 would always be higher priority, but EDF, the earliest deadline for scheduling, would actually check for which task is having nearest deadline, and based on the nearest the deadline, highest is the priority. It would check on runtime as the tasks are being executed based on the adjusted deadlines, so it would assign the priority, and that's what has happened in this particular scenario what we discussed here. That's why preemption is not happened for P2, rather P1 is waiting in the ready queue. Okay, so unlike rate monotonic or RM algorithm, EDF scheduling does not require that the processes should be periodic, or they must process or require constant amount of CPU burst cycle. So there's no assumption for it. Only the requirement is that the process announces its deadline to be scheduled when it becomes runnable. It says that this algorithm, whereas RM says that it is an optimal algorithm. If RM is not able to, schedule something, no other algorithm can schedule it. But EDF is much better because it's more dynamic, and it gives better CPU utilization. But in practice, it is impossible because CPU utilization, then there is a cost of context switching between the processes and interrupt handling. So 100% is never an obtainable number for each and every algorithm. Then we have another algorithm, that is proportional share scheduling. In proportional shares, we have T share cycles. So we have T share cycles, those have to be shared by processes. Now each would be given N share, and based on this, that each application would be sharing only, this is fixed quota basically. So based on, like, there are N cycles available for the CPU, each task would be assigned the number of cycles. Like as we move forward into real-time system, go to sporadic task and other tasks, so we always preserve some quota of CPU cycles, so that whenever a task is coming, sporadic task is the one which is abrupt, aperiodic, and has a hard deadline. So hard deadline is the one, if it is not executed by that deadline, it means it is never executed, because there is no outcome after that. Like, let's suppose if the automatic braking system, or there's an automatic landing gear, if that task is basically for aircraft, it has to open its wings and the tires and all that. If those tasks are not executed by the time, then there is the results would be very hazardous. So that is very dangerous results are there. So those are called hard deadline tasks basically. So if they're not running before the time, then there is no meaning of running them. So normally the mix and match of algorithms are, as we discussed in the previous non-real-time algorithms. So first comes first serve, shortest job first. We actually use mix and match of algorithms. As I always say, the algorithms, each algorithm has a biasing toward one particular type and class of problems and the processes. So there are multiple kind of algorithms those would be running at same time in your system to run a different class of algorithm. So one scheduling algorithm is which gives the share how much number of cycles, how many number of cycles one process would be getting. So this is that. Then we have the APIs for scheduling. So this API is basically stating you can actually use these functions to actually set and get the scheduling policy for your thread. So this, based on this, you can actually set. So here I actually showed you earlier that there are three different scheduling policies which are available for Linux. One is scheduling FIFO, other is scheduling round robin, and then there is scheduling other if we want to schedule using a different algorithm. That is there. So these are the APIs, that the functions which we can use to set and get the results. Let me show you if I can. Yeah, so for this particular program, what we are testing is what is the scheduling policy used for this operating system. And once we get it, we can change that. Here you can see we are trying to get the policy. And if we see which policy is currently being used for the processes, we can change it if we want it. We can change that to a different scheduling policy here. And otherwise, if it is good, then we need not to change. So for each and every thread, we will see which scheduling policy would be executed. So these two algorithms functions are there. Those would be helping us to get the information for the current scheduling policy and set the different scheduling policy if we want to set. So for this system, scheduling policy is this. It is others. So as we have seen using chart, what was the number of the process? So this is where we can see that all threads are running using scheduling other for this particular system. Now we can set and we can use a different policy for scheduling policy for the processes. Okay, and yeah, Linux kernel basically has improved a lot over the time. So previously it was not that efficient in handling real-time jobs, or was not fit for SMP systems. But as there is a version change, so basically it is more preemptive and priority-based scheduling fit for SMP, perform load balancing, have processor affinity, and but it has a poor response for interactive process. So over the time it actually improved a lot. So real-time scheduling is possible using Linux system. So there are two types of tasks which are running. One is basically your the real-time task, and other are normal tasks. So if you remember, we saw the nice value. So the nice value for the processes is because they are running within that particular nice value is nice process. Nice process is the one which can change its priority to accommodate other processes. So we can set that nice value for a process so that it become a lower priority task, or it become a higher priority task. So it means that we can adjust the nice value of a process. So the nice value would -20 would map that to a global priority. Now priority is different than the nice value. So from the nice value, we calculate the priority value. So if the nice value is -20, then the priority is 100 for that particular, the global priority is 100 for that particular process. If the nice value is 19, then the global priority for that process is basically 139. So we can see the real time has given a quota of this particular range. So every process that is scheduled by the kernel with priority from 0 to 99 is a real-time process, whereas normal processes are basically having their scheduling is based on the limited to this particular range. And then we have the nice values, and nice values could be changed to accommodate basically other processes. So this is how it actually works. We discussed about nice value. So we can see that the currently running commands and their nice value here. So the nice value for this is 0, and this is for -20. So this process is basically all those who are basically on -20, they are having a higher priority than other processes like this. This process has a lowest priority from the range. This has a highest priority than my +19, but lower than -19. So these are the process ID and the parent process ID. So this is how we can actually see the priorities of the processes in the system. So Linux supports basically two type of priorities. The scheduling algorithm that has been implemented for version 2.6 is completely fair scheduler. It has scheduling classes. So two classes are there. So as we discussed, one is default and other is real time. The scheduler picks the highest priority task in the highest scheduling class, and then it basically looks for if anything is pending in the real time, and then it moves to normal classes. Quantum is released based on the nice value. So based on the nice value, if lower is the value, higher is the priority. And it has target latency, which is basically target latency is it adjusts the time quantum based on the jobs which are available, and the interval during which the task should run at least once, that it creates a target latency. And from this target latency, each job is allocated to CPU by the proportion, and proportion would come based on the priority that is for each and every process. The target latency can increase if, say, the number of active tasks increases. So that's basically it is fixing not fixing the quantum, but varying the quantum. The other thing is each CFS scheduler maintains the virtual runtime that is called this variable vRuntime, and this is associated with the priority of the task. So associated with the decay period, if the lower the priority, higher is the decay rate. So for lower priority, decay rate would be higher. So this value, the variable vRuntime, would be higher for low priority tasks. And based on to decide which task to run, scheduler pick the task with lower virtual runtime. So you can see if the task is having lowest priority, then vRuntime would be higher, and if the task is of highest priority, then the vRuntime would be lower. So for scheduling, scheduler would look at this particular variable to schedule or allocate the CPU to the CPU to the process. So this is how this CFS scheduler perform its duty for CPU bound and IO bound tasks. So CPU, when we talk about IO bound tasks, they have smaller CPU burst cycles. So we can give IO bound a higher priority than CPU bound tasks. And this is we have already discussed. CFS defines the load of each thread as a combination of thread priority and average rate of CPU utilization. So based on this, CFS count the load, and this count would be added for each task which is available in the queue. So if a thread has higher priority, yet it is mostly IO bound and requires little CPU, then it is considered low load onto the CPU. So the low load means that the IO jobs would be considered as low load onto the system, similar to a load of a low priority thread has higher. So this is basically combination of two parameters those considered for calculating the load of a task, and we add up all those loads together to find out the load of approximate the load of a CPU. And there are then this information is shared with other multiprocessor systems. So if somebody finds that this particular CPU is, there is a protocol for that. If that protocol finds that CPU1 is overloaded, then there are two approaches. One is push migration and other is pull migration. So in push migration, CPU1 would push the sum of the task to other processor. In pull migration, some other free CPU would actually ask and take some task from the CPU1 queue, and this is how basically the load balancing would be actually happening using CFS scheduler. Also, it basically divides for NUMA type multiprocessor architecture are split into domains. So the first level of a domain is because we know that they share the cache tree. So here you can see L2 cache particular set of nodes. So what I mean to say is that the CFS algorithm actually converts the NUMA type nodes into domains. So each domain would be having different codes which are working on different level of memories. Like here, L2 cache memory they are sharing, and then L2 this domain is sharing, and domain 1 and domain 0 are sharing L level 3 level of cache. So basically, based on this, the scheduling would happen. So if the scheduler has to change or balance the load of core 0 and core 1, they'll first try would be that it should be within core 0 and core 1. If it is not possible, then it will go to domain 1. So there is a level how the procedure of load balancing would happen, and that is what being used by CFS algorithm. Now for the CFS here, we there is a red black tree. This is a balanced binary search tree that is created based on V runtime. So V runtime, as we discussed, is lower for higher priority tasks, higher for lower priority tasks. And whenever this is lower, so it is a balanced tree. So V runtime, when it is lower, it would always be added onto this particular time. So the task with smallest value of V runtime would always be added to, because it's a balanced binary search tree. So it will be added here, and scheduler would always pick a task which is allocated here. So this is how your queue is basically maintained for CFS, okay? Rather than just a normal linked list. It's basically your binary search tree format which is being used for CFS. So this completes your scheduling, where we discussed about few scheduling algorithm that combines the normal task scheduling. Then we discussed about real-time scheduling, two real-time scheduling algorithms, very important algorithms, RM and EDF. EDF is dynamic priority scheduling algorithm. Then we discussed about CFS, which is used by Linux system. It basically has all the functionalities which we discussed, and the advanced functionalities to actually cater multi-processor environment or NUMA type architecture. So it can handle all those scheduling requirements which are there for different type of architecture. So it is basically